Today we have Dr. Keegan Moore from Georgia Institute of Technology, and he'll be giving a presentation on his studies on data-driven identification and reduced order modeling of strongly nonlinear structures. Whenever you're ready, Keegan, the floor is yours.
Awesome. Thank you so much. Just get rid of that. All right. Yeah, thank you everyone for coming this afternoon. I'd also like to thank all of the students in my group that have worked on the research I'll present here, as well as other research as well as all of the sponsors that have supported my work in general, and especially the National Science Foundation and AFOSR for supporting the work that's presented here. So the U.S. industry spends about $2 billion every year on vibration testing and measurements, just for the sake of calibrating and validating computational models. However, often important nonlinear dynamics is missed during this process, which ultimately leads to the U.S. losing around $1 trillion every year. That $1 trillion comes from three major costs. The first being that of failure, where a system either breaks during operation or doesn't do what it's intended to do during operation, or it physically breaks, leading to the loss of property, environmental consequences, injuries, and potential loss of life. The second major cost is that of suboptimal designs, where structure is either over-designed to compensate for this missing dynamics, then leads to increased material costs as well as increased weight, and then therefore decreased efficiency and performance during operation. Or on the other hand, that missing dynamics could have been leveraged as a way to improve the performance of the system during operation. Then the third major cost is that of missed structural health monitoring opportunities, where this missing dynamics shows up during operation that then leads to false positives and triggers maintenance and replacements that are not needed, and therefore drives up costs through that. And on the other hand, this missing dynamics could have been leveraged to do SHM as well. So if the US loses $1 trillion every year, it raises the question of, well, why is this nonlinear dynamics being missed? Why is it not being incorporated into engineering designs? And the answer is simply that in general, practicing engineers are just not equipped to handle nonlinearity and nonlinear dynamics. And so in order to overcome this, our vision is simply to put nonlinear dynamics into the toolbox of every engineer. And we intend to do this by leveraging data, machine learning, and autonomy in order to remove barriers for utilizing and understanding nonlinearity. And our approach is three-pronged, starting with looking at how do we do measurements and testing in both laboratory and operational settings, and then bringing in autonomy and AI into this process so that we can do autonomous and smart measurements, and then taking the information and the data produced by that and sending that into techniques for autonomous model discovery and validation, model updating, et cetera. And then lastly, linking these two things together so that we can have feedback mechanisms so that the testing and the data produced during testing gets better over time at the same time as the models themselves get better and update to account for changes in the system over time. And then the third prong is to look at how we as humans interact and engage with data, and then bring in tools from virtual reality, augmented reality, et cetera, and leverage those as another feedback mechanism in order to drive this entire process. And I'd just like to say that this vision and our approach really aligns well with the Sustainable Development Goals set forth by the United Nations. I've highlighted 6 of them shown here, but it certainly aligns with more of the other 17 as well. So this presentation is going to focus on our research on data-driven identification and modeling of nonlinear structures. So we're going to be focusing really heavily on this autonomous model discovery side of things, and then built into that is also the process of reduced order modeling. I'm going to start off by talking about our technique called the energy-based data-driven dynamics identification, or EDI. I'll then go and talk about another system ID method called system identification via validation and adaptation that leverages AI. We call this SIVA. And then last topic will be on our work on reduced order modeling of bolted joint loosening. So starting off with EDI, this is a technique that leverages analytical mechanics in order to identify governing equations from experimental measurements. So we're thinking about concepts like conservation of energy, Hamilton's extended principle, and Lagrange's equation. And Eddy will directly leverage conservation of energy and Lagrange's equation applied to experimental measurements to extract equations of motion. So in Eddy, we are coming from the viewpoint of we have access to anything that we can measure, so the mass and generally time series response data, both accelerations, velocity, and displacements. And our goal is to come from this stuff that we can directly measure and end up with some mathematical model that approximates and reproduces that experimental measurement. Eddy is split into two phases. The first phase focuses on creating a model for the dissipation. It leverages conservation of energy in order to find the dissipated energy by the system, and then we leverage that to then find a model for the internal damping of the structure. We then pass that information into phase two, where we leverage Lagrange's equation and Lagrangian mechanics in general in order to find the internal conservative force acting on the structure. And we then leverage that information to build a model for the stiffness of the system. Or you can combine these two together and then form a mathematical model for the system. And then this will allow us to then simulate and reproduce those experimental measurements. I'm going to walk us through Eddy using a single degree of freedom simulated system. I'm then going to show us two experimental cases. We're going to consider generally single degree of freedom with a general equation of motion with some damping term or dissipative term shown with B here, and then some internal elastic stiffness, and then some generic initial conditions. In this simulated example, I'm going to use a specific equation of motion to just demonstrate how this technique works. In this case, we have a linear viscous damping term, and then we have a secondary nonlinear damping term. We have a linear stiffness and then a cubic nonlinearity shown here. Parameter values are listed below. We're going to apply an initial velocity of 5 meters per second to this system and generate a simulated response. I show here the displacement of this oscillator, and you can see how over time its frequency is changing, and we've projected this into the wavelet domain using a wavelet transform. This provides a time frequency representation of the signal content where the darker the shading, the higher the energy content at a particular time and frequency. And in this case, you can see a single band, and there's maybe very slightly another band up here, but really this dominant band here represents the dominant natural frequency of the system, and it shows how it decreases over time due to the nonlinearity in the system. Okay, so going into Eddy, we start by computing kinetic energy. This is something we can do directly from data. We know the mass and we have a velocity, so we can compute kinetic energy directly. We'll then apply conservation of energy and leverage conservation of energy to find the dissipated energy shown here. What we realize is that whenever the displacement is zero, we assume and assert that the potential energy is zero. And as a result of that, all of the mechanical energy is stored in kinetic energy. And so we can leverage this as a way to track how energy is changing the system over time. We're going to say that these gamma i's are the times where the potential energy is zero. And at those particular times, we can leverage conservation of energy to find the dissipated energy at those particular instants in time, as shown here. One additional thing is that we're going to shift time to start at the very first time where the potential energy is zero, such that we can use that as our initial energy and compute changes over time. Once we have this dissipated energy, we can then go and propose a mathematical model for the damping in the structure. You can see that the dissipated energy is related to that model through this integral term right here. We'll expand this into some scalar parameter multiplied by a function. Generally, this would be like x dot or x dot cubed, etc. And in each of these model terms is going to have their own coefficient. We can take this, we can plug it into conservation of energy, and then expand this into a linear system of equations for every gamma I time, and then use this to solve for the unknown coefficients from our damping model. That's exactly what we do here. I show here again the exact system. The model that we're applying in this case is shown down here. We went all the way up to an x dot cube term. We still include that mixed nonlinear term below. Top left, I show a comparison between the model and the data itself. We can see a good agreement there. If we look at the actual coefficients identified by our model, they are nearly exactly what they should be with very low percent errors shown here. And keep in mind, this is simulated, so there's no noise, there's no measurement error. So we should expect to get a really good result here. Moving forward, we're going to use this information. Now that we know this dissipated energy, we can leverage this to go and compute the mechanical energy, that is the kinetic plus the potential energy. That's what we show here. We compare our data approach with the exact. Once we know mechanical energy, we can take this and leverage it to compute a Lagrangian in the system. We don't know this potential energy exactly yet, but we can manipulate conservation of energy and what mechanical energy is and define a Lagrangian in terms of kinetic and the mechanical energy in the system, and then use that to compute this Lagrangian. And at this point, we now have a Lagrangian time series, and we're able to go in and apply Lagrange's equation to it. And so we're going to apply Lagrange's equation to that Lagrangian in order to compute a conservative force acting on the system. We start off with just the conservative term in Lagrange's equation. This is a partial derivative, and we're applying this to numerical data. We have to then do a chain rule, and then that leads to the following expression here, where we can now compute everything here using measured data. We already know the acceleration of the mass, and then we can compute this derivative numerically using just numerical derivatives. And this then leads to the conservative force, as shown here, which we plot as a function of time. We compare between our database approach and the exact approach, and there's a very good agreement between the two. With that conservative force, we are now able to go and plot it as a function of the displacement and get a restoring force plot. This then allows us to interrogate the type of nonlinearity that exists in this system. This is a smooth nonlinearity, and so again, we get a very nice smooth nonlinear restoring force. Based on this information, we can propose a model for the system. For example, if you were to have a clearance nonlinearity or some type of bilinear, you would see sudden shifts and changes in the stiffness, and therefore you would then be able to use that to propose a different type of model. For this system, we are going to use a fifth-order polynomial in the displacement, with the only two terms that are actually really there are the linear term and the cubic term. We can go and just fit this model to the data using standard curve fitting procedures. You can do advanced optimization if you want. Whatever you would like to do in order to identify this, it can be applied in this context. We can see that for the two parameters that are really in the system, we actually get really good values. We get really close to the exact parameter values. For the other three parameters, K2 is very, very small, so it can be effectively neglected. The other two are also very small because, again, this displacement is cubed, or sorry, for K4, the displacement is raised to the fourth. K5 is raised to the fifth power. So that quantity is extremely small. And so even though these are not necessarily small parameters, their effect and the force they produce is extremely small. Okay, so we've shown that for the simulated case, we can recover the parameters that are truly there. We're now going to take a look at how does this work in experimental applications. We're going to consider here a nonlinear oscillator with a smooth nonlinearity and weak damping in this case. The oscillator is composed of an aluminum block here for the mass. It uses a pair of steel flexures, one on each side with a big cutout in it. These flexures add a linear grounding stiffness to the structure. And then there are a pair of steel wires that are clamped on this side. They pass underneath this mass, and they're clamped in the center here, and then they're clamped on the other side. These wires add a strong geometric nonlinearity to the system, as well as a small additional linear stiffness. Here's the experimentally measured response for this system for a force of around 670 newtons. You can see that indeed here, looking at the wavelet transform, we do get this nice transition in the frequency over time. And this response lasts for over, here you would see over 45 seconds. In the actual data, lasts for over a minute. And that's where this is extremely weak damping. So we should be able to extract a lot of data from this. And indeed, we go and we compute the kinetic energy. We find the times where the displacement is zero. We pull out the kinetic energy at those times. And then we can clearly see how the dissipation is occurring through this kinetic energy. We can apply that conservation of energy expression and then compute directly the dissipated energy. As you can see right here, there's actually a little bit of like an oscillation in this dissipated energy, interestingly enough. We can go ahead and we propose a mathematical model. We're going to use the same model that we used previously for this oscillator. We're going to go ahead and do some curve fitting or a linear regression in order to identify these parameters, and we arrive at the following parameters shown here. This is an experiment, so I don't know what the exact parameters are. And again, this is also a reduced order model for the true dynamics. Nevertheless, we can see that the model does do a good job of fitting and capturing this dissipated energy across the whole time series. With that information, now we can go and compute the mechanical energy, then the Lagrangian, and then we can apply Lagrange's equation and then end up with the experimental conservative force, which I show here as a time series on the left. And then on the right, we have it plotted versus as a function of the displacement. And again, we can see that this has a nice smooth nonlinearity, which is what should arise for this system with those wires. The wires introduce a smooth nonlinearity. Based on this, we'll go and fit a fifth order polynomial to this data, and we'll get the following set of parameters. Again, this is a reduced order model for an experimental system, so we don't know true parameters, but we can see that it does a good enough job of matching this restoring force plot as well as matching the time series shown there as well. Now that we have a model for the internal conservative force and one for the non-conservative force, we can combine these together and form the governing differential equation for the system shown here. And then we can take those experimentally measured forces, apply them in. Sorry, this is set to 0, but it should be equal to some f of t, which is the impulse applied by the hammer. We take this model, we simulate it for the input force, and then we do a comparison with the experimental measurement, as shown here. And indeed, you can see that for the case we used to do the identification, the 670 newtons or so, we can see that the model does a good job of reproducing this response. So the question then is, does it do a good job when you apply it to a different data set? And in here, we're showing a comparison with a much higher force, almost double the initial force that we used for the identification. And although we do miss a little bit in the amplitude in the beginning, the overall response is relatively good and matches the behavior in general, especially if you take a look at the wavelet translants, we do a good job of capturing that change in frequency over time. Not shown here, but we also compare it to lower input forces, and it does a good job of matching the experiments down there as well. So eddy also extends naturally to a forced response cases. And so in this case, we're still going to apply conservation of energy. In this context, we end up adding an additional work term done by the external force. And so when I say forced response here, we're really thinking sustained forcing from like a shaker or some other external element. We introduce this work term shown down here. We can then look for the times where the displacement is 0 and find where the potential energy is 0, and then express an equation for the dissipated energy that depends on initial kinetic, the work done, and the kinetic energy at times gamma I. In the context of operational cases, we may not know an input to the system. This W term can be pulled on over to the other side, and then you can leverage this to do modeling of inputs as well. That's a current thing that we are working on, and I'm not going to show any results for that. Instead, we're going to look at a case where we know what the input force is, and we can compute W directly. We're going to look at that same oscillator with a few modifications. First of all, it has a different pair of steel flexures on it, and it has different set of wires on it as well. So the stiffnesses have changed on this system, although the damping should be relatively similar. We're going to force it using a TMS Smart modal shaker shown here, but rather than using a standard stinger, we're going to use a magnetic stinger in order to ensure that our input force is actually nonlinear. And specifically, it will be asymmetric due to the way the interaction between these magnets are set up. The magnets are repelling in this setup, and I'll actually let this video play here, and you can see how the shaker will drive this oscillator using that magnetic interaction force. And it's asymmetric because it has a different force when it pushes than when the shaker pulls back. Indeed, you can look at the comparison of the drive signal and then the actual input force produced by the shaker. You can see that this drive signal is very clean. It does ramp up in the beginning, and then it turns into a very nice sinusoidal. This is the input voltage that goes into the shaker, and then this is the measured force produced by that shaker. You can see here that at steady state, we have this very asymmetric force, both in terms of the amplitude, but also in terms of the profile that is arising due to that magnetic stinger. Here's what the displacement response looks like for this system. We're comparing here both the full response that includes the transients and then also the steady state response. We are saying that steady state occurs right around 10 seconds. It may occur a little bit sooner, it may occur a little bit later, but right around 10 seconds is a good shot for that steady state. Below, I'm showing the Fourier transform and specifically looking at the steady state. You can see that we clearly have a dominant peak here. This is the frequency of the shaker. And then we have all of these additional harmonics that are showing up. And that's caused by the nonlinearity, both in the structure, but also through that input force as well. We're going to use this case, which is at 0.6 volts, 12.75 hertz. We're going to use this to do the identification. Then we're going to use other cases to do validation on the final model. We apply this entire eddy approach and then applying conservation of energy, arrive at a dissipated energy for this system shown here. We have shifted time forward here just to start at the first time where the potential energy is 0. We propose the same mathematical model that we've seen previously and identify the following parameters shown down here. Now, the system has changed, so these parameters should be a little bit different than the other cases, but they should be on the same general order of magnitude. One interesting thing is that this cubic term, we actually find a value that is 0. I believe it's on order of like 10 to the minus 8 or something. So on all purposes, it becomes 0. Once we have this model for the damping term, we can then go and apply Lagrange's equation and then correct the conservative force out of it, plot that as a function of the displacement, and then we can go ahead and fit a model to that as well. In this case, we actually just stop at a cubic term. We did start by going all the way up to the fifth order term, and we found that the fifth order and the fourth order parameters, they were very small and could be neglected, leading to a better model with only 3 terms in it. All right, so I now want to show some validation results of this identified model. This is results shown here are for the same frequency that is being excited at, but for different amplitudes of excitation. And I also apologize, the model should have a forcing term added here, shouldn't be equal to 0. So here we're forcing at 0.4 volts, and here we're forcing at 0.8 volts, but at the same frequency we use for the identification. Here we get a good match in general. There is a little bit of a deviation in the amplitude, but otherwise we get a good reproduction here. One other small little difference is that there's a bit of an oscillation or model that is not as prominent in the experiment, but overall still a good result. If we switch to now looking at different frequency inputs, but the same amplitude as the identification case, we again see that our amplitude is a little bit off in those displacement responses. We can see that we definitely deviate a little bit, but the profile and the shape is very similar in both cases, both at 5 hertz as well as at 16 hertz. And so indeed, eddy can be used to identify the dynamics of an oscillator using forced response cases. We are also in the process of extending eddy to multi-degree of freedom systems as well as continuous systems. We are doing this through a component decomposition. So again, the idea is that we have a set of measurements. In this case, we would have multiple measurements per degree for many degrees of freedom. And we want to end up with some validated mathematical model at the end of the day. So we start by decomposing each of the signals into components. Shown here, we are specifically using the wavelet-bounded empirical mode decomposition. The main reason for this is that the output of the wavelet-bounded EMD is harmonic time series components that can be treated as modal oscillators. We can then apply eddy to each of these components directly, treating them as their own individual modal oscillators. I mean, that's exactly what we do. We apply eddy to these components. We split up into the same phases. We start with finding kinetic energy, finding the times where that potential energy would be 0, leveraging that to find dissipated energies, then using that to find a damping model. We then go to phase 2, where we can leverage Lagrange's equation. We can also leverage Newton's equation, and you could also leverage conservation of energy. There's many things you can do here. We can then fit a mathematical model to the stiffness term for that component, and then the output is a damping model and a stiffness model for each of these components, in a sense of that treating them as modal oscillators. We can then, a nice property of EMD then allows us to actually directly sum these components together to form the internal non-conservative force and conservative force acting at each degree of freedom. And once we know the forces at each degree of freedom, we can then go and fit models to that and determine what fit reduced order models to reproduce those. And this then leads to this validated model. This is ongoing work, and so I won't show too much more about this. And actually, with that, we're going to switch and go take a look at our system identification via validation adaptation, or our SIVA technique. So something that we have noticed, and this is also true in our own research as well in our techniques, is that majority of system identification methods don't do validation of the model simultaneously. They take a single data set and then they will use that to identify a model. And then you have to go and separately do validation with other data sets. And this is true of both Eddie, of Cindy, and other techniques as well. And so we wanted to come up with a way that we could validate our model at the same time as identifying it, and then leverage this as a way to do continuous model updating over time. We came up with what we call SIVA. Again, we're going to start with things that we can measure, and we're going to want to eventually end up with a validated model. The idea is that we're going to leverage noise to generate a series of parameters, and I'll go through how we actually do this. We're going to use those parameters to generate a response, and this will ultimately lead us into being able to produce a validated mathematical model. So this whole idea comes from what are known as generative adversarial networks. These are a machine learning technique that was created to generate images. Anytime you see like a deep fake, a generative adversarial network could have been used to generate those. There are now other techniques as well that do this. But the whole basic idea is to create a competition between neural networks and use that to drive uh, and improve over time. In our context, we're going to use some digital model, a finite element model, or a reduced order mathematical model, or even a neural network itself. We're going to use that to generate some type of response data. We're going to then compare that response data with real test data through a discriminator. If the discriminator can tell that generated data is fake, then this tells us that our model does not reproduce the test. If it cannot tell the generated data apart from the real test data, then it tells us that the model is reproducing that test data. And so then we can then incorporate additional neural networks in order to translate the outcomes of this discriminator into changes in the parameters of our model. And then training of this entire GAN type approach will lead into a digital model that is identified, but also then validated against additional test data. All right, so I'm going to go in and talk more about the way our technique actually works. We start off with a set of real training data. This is experimental measurements that we're going to use to do ultimately a physics-based updating of our parameter generator, and then we'll have a separate set of data that we'll use for validation. We're going to plug this data into some existing equation of motion that has some unknown parameters shown here. We will then use a parameter generator network that will take in a vector of random noise and then map that noise into generated parameters. The reason we want to use noise is because that every time we iterate on this parameter, we're going to change this noise, and this will allow us to ultimately generate distributions for these parameters so we can do a little bit of uncertainty quantification at the same time. Taking that, we can plug in our parameters and our training data, the displacement velocities, into our model. We'll generate some acceleration term, and then we can compare that with the exact acceleration from the measurement. And this will be our physics-based loss that will go into this parameter generator to improve it. Then we'll take real validation data. So this is additional test data that we're using to do specifically validation. We'll plug displacement velocities into our model to generate a validation acceleration. And we'll plug that into this discriminator as well as the validation accelerations and feed that into the discriminator, and then use this loss to update both the parameter generator and the discriminator itself. And this places these two networks into competition with each other, where the parameter generator is trying to produce parameters that are so good that it can fool the discriminator, while the discriminator is trying to become smart enough that it can always tell the generated output from the real inputs. And these are the loss. I'm going to skip over that. We're going to demonstrate SIVA using two examples. The first is a two-story tower with a nonlinear stiffness coupling the floors. We have what we call the linear oscillator as the bottom floor. It is linearly coupled to the ground with a pair of steel flexures. And then it is non-linearly coupled to the second floor that we call the nonlinear oscillator, or the LO and the NO. The NO is connected to the LO with a steel flexure shown here. And then there's again a pair of wires that runs underneath that's clamped here, clamped on the other side, and then also clamped to the NO in the center. And those wires are adding the strong nonlinearity to the system. We're going to use three data cases. The first is a 530 Newton impact applied to the top floor. That we're going to use for the training. And then the other two cases also applied to the top floor are at 37 and about 900 Newtons. On the right here, I'm showing the displacement response of the LO and the NO. In the background, the LO actually has a lot of beats going on it. It oscillates quite a lot, and as well as a slowly modulated amplitude. You unfortunately may not be able to see that just due to the way the sine curve kind of covers that up. But if you look at their respective wavelet transforms, we can see that in the LO, we have a nice solid line here. This one actually does increase a little bit if you go backwards in time. And then again, we have another band right here. This band has these beating patterns. So there is an indication that there's some type of interaction between these two. It's some type of nonlinear interaction. NO has just that single component at low frequency. And below that, I'm showing the Fourier transform. All right, so we're going to model this system using these two equations shown here. This particular experimental system came from previous work where we had established a baseline model already, and we're just using the same model structure as was used in that paper in order to do this. One thing to note here is that we're using a generic polynomial here, where alpha is the stiffness coefficient, and then beta here can be any real number. It does not have to be an integer value. We'll apply SIVA to this system using this model, and we find that it generally converges quite rapidly. Overall, you can see that the losses converge relatively fast. The discriminator gets pretty close to its theoretical value. Parameter generator loss starts pretty high, then drops, and then drops again down here. But we're really interested in parameters as shown here. When we say that SIVA converges, we're really looking at the parameter values, not necessarily the losses themselves. We're looking at when do these parameters converge. And that happens around about 900 epochs. And we did run for longer than 1500, just showing 1500 here. You can see that all of the parameters have effectively converged, and maybe it will only change minorly. An interesting thing is that this beta parameter, although it could be any numerical value, it actually settles down to very close to 2. And so that actually leads to this being effectively a cubic nonlinearity. So that's an interesting outcome of this. Once we have modeled and once we've trained this network, we can take the parameter generator and run it for 1,000 iterations where we plug in 1,000 different noise vectors and produce 1,000 different parameters, or as many as you want. And then we can use that to quantify the distribution of the output parameters. And that's exactly what we've done here. And then just for simplicity, we've fit Gaussian distributions to this data, regardless of whether that is, makes sense. It doesn't really make sense in the case of beta here, but beta also has a very narrow distribution in general. But it does fit the other parameters really relatively well. This is experimental system, so I don't know exact values, but I can say that the red line is the mean value, and the gray or the green shaded area represents 95% confidence intervals. And so this method also allows us to do a bit of uncertainty quantification in the parameters themselves that you could then go and use to do a larger uncertainty study as needed. You can then take this model and you can use it to reproduce experimental responses as shown here. We also applied Cindy to this system just as a comparison point. And in general, we found that SIVA produces a model that does better. And it does good in both the time series as well as in the wavelet transforms and the Fourier domain. All right, we're going to look at one more example. This is a simulated case of a cantilever beam with a nonlinear nonlinear tip attachment. This tip attachment adds mass. It adds a linear and nonlinear stiffness, and also a linear and nonlinear damping term to it. There is also a distributed static load W in here. The setup for this is that we're looking to take an existing linear model and then update it to account for missing physics that is introduced by adding nonlinearities to the system. So we model the system using finite elements, and then we apply a Guggenheim reduction to that system that represents our linear base model. And then this tip attachment is introduced, and our goal is to identify all of the parameters CL, KL, C, and K. We assume that we know M because you can measure mass directly, so we're not trying to estimate M either. It's just the parameters that you may not be able to measure directly. Again, we're going to use three different data sets as shown here. We're going to use two for validation, one for training. In this case, we have a different impulsive input from f of t, but we also are applying a different static load w in each of these cases, just to vary the data up and see if we can do better with that. Looking at the wavelet transforms, you can see that this nonlinearity actually affects all of the modes. Each of these bands represents a nonlinear normal mode in the structure, and it has a wide global effect on the response of the structure across all of its modes. Okay, so we do run and train the system. You can see here how it converges very, very fast. Generally around, we say it converges about 200 epochs. All of the losses approach very close to their theoretical values. This physics-based loss drops very rapidly as well. But again, we want to look at parameters, and you can see here that the parameters have converged, we would say, probably around 160 epochs, although we keep running it to ensure that we've achieved the best model. And this is a relatively fast process. This whole running of 1,000 epochs takes, depending on your computer, can take roughly about, I would say, maybe like 20 minutes, maybe less. It is a relatively fast process. Here we can show a comparison between the identified parameters and the exact values. Again, running 1,000 iterations through the trained parameter generator network, and then fitting distributions, looking at the mean values, and then also shading 95% confidence intervals. We can see that we do really well for the linear and the nonlinear stiffnesses. We're a little bit off for the damping terms, although the bounds or the variation in the variance in the damping case is also very small as well. Okay. All right, so we can take that identified model and we can show that we can reproduce the validation data. We can also reproduce the identification data, but we're really looking at, does it reproduce validation data? And indeed, it is able to do that both in time series and in the wavelet transform. And then lastly, for this system, you can compute analytical static solutions for different distributed loads. We did that shown here. So the black line represents the actual analytical solution for this system. The black circles represent the static equilibrium that a time response simulation converges to after a long time. And then the red X's represent that same long time simulation solution for the identified model. And you can see that these are all in agreement across different static loads applied to this system. Okay, so CEVA is also being extended to different applications. We're currently applying it to forced response, where we're learning different parameters. Just an example, using that forced response, where in this case, we know what that forced response is. We've gotten good results from that for simulations, and now we're heading towards applying this in experimental systems. We're also working towards applying this to operational cases where you may not know the inputs to your system, and so you may want to produce a model for those inputs. And we're looking at how we could leverage this technique to do both mathematical models as well as maybe mixed neural network models where you're using a neural network to model the inputs, but then you're using mathematical models for the dynamics of the system or vice versa and so on. And then we're also very interested in leveraging CEVA to do continuous model updating, so to track how parameters change in time, particularly when discrete changes happen, something breaks, something suddenly violently ruptures or so forth. But then also heading towards more gradual changes over time as well. So far, we've applied this to cases where we have sudden abrupt changes in this particular 2-DOF system. We have time varying K3, time varying alpha term here. In this particular case, we just led to abrupt changes at particular times. When we say epochs here, this represents continuous application to data, with the idea being that at some point you get a new set of data that you now want to run this CEVA technique on in order to check that your system is up to date based on the new data. With that, we're going to switch to topics and go and talk about our work on reduced order modeling of bolted joint loosening. I want to start by saying that loose bolts are a universal problem that affects everyone. In 2013, a single bolt loosened that led to a train derailing in Paris. This led to 6 deaths and dozens of injuries. The pictures shown here come from the actual crash report from this incident. And in fact, on the right here, I've gone ahead and circled the component that failed. It's this fish plate shown here. And there's actually a nut circled up here. And then you may not be able to see this, but there's a bolt and a nut down here as well. Again, a single bolt loosened and caused this failure. In 2016, a single bolt loosened led to another train derailing, this time in Oregon, and this derailment released 42,000 gallons of crude oil, but 20,000 gallons of that went into local water supplies, unfortunately. But loose bolts are not just a problem in extreme engineering cases. In fact, a 2019 survey of 109 playgrounds found that there were about 30% of them had loose bolts and were dangerous to children. This survey was performed in the US Midwest. So this is not just far away from home. This is close to home for many of us. In addition to that, screw loosening and bolt loosening is very common in biomedical applications. In fact, around 33% of spinal screws will loosen within 2 years, ultimately requiring corrective surgery every single time. This is common in dental implants as well, except in that context, it's about 50% will loosen within 1 year, and again, corrective surgery is required. I'm going to let this video play for a moment, and hopefully you all can see that. I don't know how well that goes through Zoom. In this case, this tire or this wheel is ejected from the truck, hits this vehicle, and that vehicle completely flips and is just smashed to smithereens. Fortunately, everyone was okay in this incident. Everyone walked away, but around 23% of all car service issues are caused by loose bolts, and around 12% of new cars have loose bolts in them when you drive them off the lot. In fact, even NASA's $10 billion James Webb Space Telescope was delayed due to loose bolts and screws. And in this case, they could not prevent loosening. They tried Loctite, locking nuts, etc. They tried everything they could think of and nothing worked. They had to go back and completely redesign the joint in order to prevent this loosening, which led to a large, massive delay in this project. Okay, so let's talk a bit about current modeling methods. And in my opinion, while very elegant and interesting, they're just not suitable for simulating long-term behavior of real structures with many, many joints, with many, many bolts. There are two really main methods. The first is high-fidelity finite element models, where you model the threads in both the nut and the bolt itself. You incorporate nonlinear contact mechanics between those threads. And this leads to hundreds of thousands, if not millions, of elements in a single bolt and a single nut, leading to extremely long simulation times for generally only maybe one or a few cycles of motion, always for sinusoidal as well. The second major approach is to use analytical models where you're deriving effectively the equations that govern loosening. These are very, very elegant, very, very fascinating and interesting, in my opinion. The downside is that they have generally a lot of parameters, which is maybe to be expected for this type of problem. But they also inherently make assumptions about the type of motion. They inherently assume that there is a sinusoidal displacement across the joint, and then they make several other assumptions as well. And generally, I mean, real structures experience random vibration as well as multi-harmonic vibration. They're not just forced at a single frequency typically. And so while very elegant and interesting, they're just simply not suitable for modeling these types of systems. So our modeling approach asserts that the bolt tension is itself a dynamic degree of freedom, and it has the power to control the behavior of the joint itself. I'm going to make a few observations here, and I'll go a little bit fast over this. The first is that there's some theoretical maximum stiffness that you can achieve by tightening your bolt. This is generally less than if you were to have a solid member and no joint at all. We would assert that we would never necessarily achieve this stiffness, but just that it exists. The second is that when the preload is low, it's very easy to increase it. When the preload is high, it becomes much harder to increase it. So you get this diminishing returns effect where the more you put into it, the less you'll get back. For damping, we kind of see an opposite trend of stiffness. At very low preload, the damping is going to be very strong. And then as you go to higher preload, that damping is going to become weaker. And eventually you're going to have, in this case, you would consider it a diminishing loss over time, meaning that you're going to lose less and less effective damping as you tighten it. And there should be, if theoretically, some minimum possible damping, again, associated with a solid member. We'll talk about bolt tension next. Generally, when you observe loosening in an experiment, there's often an oscillation that occurs where the bolt will tighten a little bit, then loosen a little bit, then tighten and oscillate between those two. But generally, it will loosen more than it tightens, and therefore there's this net loss of tension. We split this up into two components. We call one a static component, or you can think of it a non-oscillatory component, and the other one is an oscillatory component. And our assertion here is that the summation of these two is what leads to this loss of tension. We're going to model this net loosening using a first order ODE here. We're just interested in capturing this long-term net loosening over time. And we're going to use the model shown here. We're going to apply this to a pair of oscillators that are connected by a single lap joint. We have a large oscillator and a small oscillator. Large oscillator is made of stainless steel. It is a lot of mass, almost 10 times the mass of the small oscillator. They also have drastically different flexures so that we have a low natural frequency in the LO and a high natural frequency in the SO. We excite this system using an automatic modal hammer shown here. Generally, here's a view of our lap joint. We have a single bolt inside there. That bolt is instrumented with the strain gauge, and we're able to measure the strain as we tighten it or as it loosens, and we can map that into the tension. We're going to look at three different, we're going to implement our approach using three progressive experimental cases. We're going to start by testing the two oscillators in an uncoupled configuration. This allows us to determine the underlying linear dynamics of each oscillator. Each of them just acts as a simple damped harmonic oscillator without the bolt in there. We apply just an impact to each of these and get a frequency response function, and then we fit just a linear model for this system. Later on, we did find that this LO actually is a little bit nonlinear, has a little bit of a nonlinear damping associated with it, but we're going to treat it as linear in this case. And also, you can see that their frequencies are roughly 10, an order of 10 in difference in magnitude. The second testing we do is what we call coupled testing. This is where we input the bolt, we insert the bolt, we tighten it to a particular tension, and then we apply a very light impact with the goal of exciting the system in a linear regime and without changing the tension in the bolt as well. Indeed, you can see that we get a relatively clean oscillation. More importantly, the LO and the SO have the same exact displacement, and this means that there is no relative motion between them, and relative motion was what drives loosening these systems. We can also take the FRF and then fit a mathematical model, or fit a natural frequency and a damping ratio to that. Here's the tension taken from that experiment. In general, these tension measurements are very noisy, and we're going to be looking at means of them. You can see here that the mean is effectively the constant across the entire measurement, meaning that that input did not change the tension of the bolt. We do this across many different tensions and apply and track how the natural frequency changes as a function of tension, and we're going to leverage that to find the stiffness in the system. Okay, so you can take the 2 degree of freedom equation of motion, and you can analytically solve for the coupling stiffness shown here as a function of all the other parameters, and most importantly, the natural frequency of the first mode shown here. And so we've just gotten that first mode frequency from the previous slide, and we can plug it into this formula along with the other parameters which we know from the uncoupled testing. And we can use that to generate the following stiffness versus tension. Just to go back to our observations, we can see that indeed this is concave up, so it's much easier to gain stiffness at low tension. And then we start to have this plateauing or this diminishing returns effect, and then eventually we hit a constant stiffness as well. We go ahead and we just fit a mathematical model to this data so that we can now track how stiffness changes as a function of tension. Not too much else to say about that. Let's take a look at our damping coefficient. You can do the same thing. You can solve for the damping coupling coefficient as a function of the damping ratio of the first mode and the natural frequency of that first mode, as well as the coupling stiffness, and then all of the other parameters that we already know in the system. This is a much longer expression, but the key is that we can relate the modal properties and the coupling stiffness and use that to find this coupling damping. And indeed, we can take a look at our observations. We can see that at low preload, you're going to lose a lot more damping. And then you get this diminishing loss effect where you stop losing more as you increase the tension, and eventually we kind of converge to this flat area. We do fit a model to this as well, as shown here. And so now we have a model for how the coupling stiffness and how the coupling damping changes a function of tension. The next case that we look at is high amplitude testing, where we now hit the system with a force about 2,000 newtons. We went from 40 newtons in the previous case to now up to 2,000. And this is designed to induce a change in the tension. Interestingly enough, we find cases where we have both net tension loss and net tension gain, even at relatively the same preloads. We did this across many, many different initial tensions. And then you can split this up into two regimes. There's really a kind of a regime, probably more below about 1,000 newtons, where we get first of all, we get large changes in the tension, but we can also get tightening or loosening that can occur. Beyond that, into regime 2, it is really dominated by loosening. This plot shows change in tension, so negative is loosening, and we're interested in this regime. We're going to focus now on looking at our model for the system. We have our equation of motion for the oscillators. We have tension-dependent damping and stiffness matrices. That comes from the coupling coefficients shown here. And then our model for the tension shown here, we have this gamma parameter that we need to identify. This is the last parameter that we need to identify. And we're going to do this by doing numerical simulations. We're going to simulate the response for an initial guess of gamma. We're going to ask, does the tension stop at the same tension that is observed, the same final tension observed in the experiment? And then if not, we'll update gamma until it achieves that. And we're going to do this for both loosening and tightening. In the case of tightening, we actually just get a negative gamma. This leads to an increase in tension. But again, we're focused on loosening here. If your bolt is tightening, it's generally not too big of an issue. And also, you're generally going to be operating in a much higher regime where loosening is more of a concern. This is just the loosening results shown here. These are all positive gammas, which would lead to a loss in tension. This can kind of be split up into two regimes as well, where you have a large gammas below 1,000, and then it kind of plateaus here as well. We go ahead and we fit a mathematical model to that that just captures this trend overall. This is raised 10 raised to the actual model itself, shown here. And then finally, now we have everything we need in order to simulate the response of this system and see if we can predict loosening using this identified mathematical model. And again, we have 3 tension-dependent parameters shown here. At low tensions, at very low preloads, our model does not actually do a very good job. And that's because the dynamics here is actually extremely nonlinear. The bolt bounces around a lot. We have a lot of pinning and impacts that occur that the model just simply doesn't capture. When we go up to higher preloads, and these are still relatively low compared to what you would tighten this bolt to. In fact, you would generally tighten this bolt up to about 10,000 or 14,000 newtons. So these are all still very low preloads. But we can see that once we go higher, our model is much better and is able to match and reproduce these changes. And generally, even though we're using tension-dependent parameters that have come from all of these different data sets. All right, so I just want to wrap this section up and talk about what we have going on. We're interested in understanding how multiple joints can interact with each other. We set up experiments with 3 oscillators and 2 joints with the goal of understanding how can we manipulate loosening in each of these joints, maybe with the goal of creating like a sacrificial joint that would loosen and then protect another joint. And we're starting to see results with that. We've also started to look at force response. We're particularly interested in looking at how we can maximize relative displacement, how we can minimize that. So looking at like an FRF, trying to find where would you get 0 relative displacement. And then we've also just taken the model that we identified on the previous page, and then we've applied that approach and then just plugged in force response and been able to find that we can, using our ROM, we can reproduce force response cases. We're not perfectly capturing the profile, but we are capturing the total loss and generally the amount of time it takes to get there. We're also looking at how can we do data-driven modeling of tension loss. In particular, everything I showed, we're trying to capture that net loss. We also want to capture these oscillations. We originally wanted to do 2 differential equations, one to capture the net loss, one to capture the oscillations. But we've now found that just using this first order equation and then having multiple parameters, delta dot here is the relative velocity across the joint. Incorporating that, we can actually do a good job of capturing both the net change as well as the oscillation in that tension. And then lastly, we're looking at using modeling that low tension nonlinearity. Here we're just using a piecewise linear model that effectively approximates micro slip, macro slip, and then pinning in the joint. And here we can see we can get a good match out of that as well. And so this is all ongoing work that we're investigating. Okay, so with that, this presentation is focused on our recent research on physics-based modeling of nonlinear structures, as well as data-driven system identification. We talked about this energy-based dual-phase dynamics, or EDDI technique. We then looked at the system identification via validation adaptation, or SIVA method. And then lastly, we looked at the reduced order modeling of bolt-to-joint loosening that we've been working on. But with that, I'd like to say thank you to all the students that have worked on this, as well as thank you to all the sponsors. And I'd like to open up for questions.
Thank you, Keegan. It was an amazing presentation. Any questions for our speaker? You can unmute yourself.
Hello, can you hear me?
Yes, we can hear you.
Hi, thank you so much for your presentation. It was really interesting. One question that I have is on the first experiment of the oscillator, how are you measuring the displacement? Are you using the acceleration information and then integrating, or do you have a strain gauge somewhere?
Yeah, that's a great question. So in all of our applications, we are measuring with an accelerometer. In everything I've shown, we're measuring with accelerometer, and then we're integrating that numerically in time domain, filtering, and then to get velocity, and then applying that same process to get displacements. You could also do this in time domain as well if you wanted. And you may have seen in our voltage joint oscillator, that thing has been speckled. So we also do digital image correlation. We just didn't do that here.
Another question. In your bold, where are you putting the strain gauge? How are you measuring that?
Great question. Let me pull that picture up. Yeah, so we actually drill. So we purchased these special strain gauges that are made specifically for this application. We drill a 2 millimeter hole into like diameter hole into the bolt itself, and then you get this coiled up cylindrical strain gauge that goes right inside there, made specifically for this application. And so it actually comes, well, the wire is a little bit off center, but the strain gauge is actually down inside here. So that also means that we may be compromising the overall strength of this bolt. These are grade 8 quarter-inch 20 bolts that you see here, but we're also not going up to the maximum tension that these bolts are designed for.
Okay, thank you.
Hi,
Any
sir.
other questions? Yeah, go ahead.
Yes. Can you hear me?
Yes.
Yes. I have a question related to GANs, your SIVA model identifications.
Sure.
You have shown like different kind of results with the different nonlinearities, and you have used a random noise to generate the to create the model identification, right? I have a question that when we train the GANs, it used a similar kind of data. So have you used a similar kind of data to train the GANs, or you have used the data from the multiple nonlinear systems and then fed it into the system so that it can learn the different nonlinearities?
Yeah,
But
that's a great question. So we are training every time we do this, we're training a new GAN for every system
okay,
itself.
okay.
It is these are not necessarily deep networks. These are generally, I mean, there are multiple layers, but they're generally pretty shallow in general. And so they are fast enough to do that. Now, scaling up to many, many degrees of freedom, like if we're thinking about like a full aircraft that's been completely instrumented, those are cases where doing some type of transfer training, would probably be beneficial. We haven't gotten up to that scale yet, but that's where we're planning and hoping to go with the Air Force.
So each individual model you train for each individual nonlinear systems, you train a GANs model, right?
Exactly. Yeah.
Okay.
And so the idea then is that this GAN would be running in real time, capturing new data as it's generated so that you can get the most up-to-date model over time. That is
Okay.
why we do this, like we train a new one every single time. And also because the cost to train it is low at this scale.
So generally, GANs is a generative model, so it can create a similar kind of data, right? So the another question is, if you train it for the similar kind of data, it will eventually learn how to make this data, right? But it is not generating anything new. So if it is not generating anything new, so you won't be able to like figure out if there is some other kind of non-linearity which can come into the system.
Yeah,
So
that's a fair question. So one of the things that we do a little bit differently is that our generator is just generating parameter values, and we're telling it what those parameters are. So a limitation is that you have to tell it the model structure. Now, you could go and change that model structure later, but you would then need to continue the training process. So we do have a little bit of flexibility there, but it does require you to know like what your model, like have a guess for what that model should be.
I understand.
Yeah.
Okay, I have one more question. Is it available online for us to use, or if we can try it?
Yeah, we have just published this, and we are intending, if we haven't already, we are going to put all of this on GitHub. And I believe the Eddie stuff is already there. We intend to put Siva on as well onto a public GitHub as well, which you should be able to find my name, or you can just shoot me an email. I'm happy to share that as well.
Okay, thank you, sir. I will write you. Thank you.
Any other questions for Keegan?
Yes, for the Eddie software, have you tried identifying a system that shows any chaotic behavior or any non-periodic behavior?
Oh, yeah. Yeah, so not shown here, but we did do that. So there's a couple things. First of all, we're now working on MDOF, so we can definitely have chaos there. In the paper that we submitted on the force response, I won't show that here. We do apply this to a simulated case where we also investigate effective noise in that, but we applied to a simulated case where we have a negative stiffness and a cubic nonlinear, negative linear stiffness and a positive cubic nonlinearity, and we investigate the behavior in a chaotic regime with aperiodic responses in that. And so it can be applied there as well. As far as experimentally goes, the system that we're applying in this 2DOF is actually the LONO system, and we are applying it to chaotic responses there. Although those are all free decay responses, but there are cases where you have internal resonances that arise as well that we're applying it to. You can see it in like this beating type pattern shown here.
Yes. Have you had success identifying the parameters?
Yes, actually. So we've applied it to this system, and it's done better than Siva, Cindy, and the original paper that worked on this. The Eddie 2DOF has actually done the best out of all of the methods we've applied. But we have not published that yet.
Okay, thank you.
Yeah, sort of related to that question, Keegan, both for Eddie and Siva, like, are there any limitations in terms of the types of nonlinearity that you have in your systems?
Yeah.
Mostly, like show polynomial nonlinearities, but I was just wondering, like if they can take care of other types of nonlinearity as well.
Yeah. So these have different limitations, I'll say. Eddie requires that your potential energy is zero when the displacement is zero. That is a hard constraint. This is true for many, many systems, but there may be systems where it's not true. That's just a hard constraint. Eddie would also not work for hard impacts where you're thinking about not just like it works for like clearance nonlinearities where you have a non-smooth change in stiffness, but when you're thinking about hard impacts where you have a change in initial, like change in an abrupt change in velocities, it doesn't work in that context. Although we've never tried it there, we have tried to apply Eddie in some contexts with hysteresis where the potential energy may not be zero. We've had relatively good results there, but we haven't fully pursued that yet. With Siva, the main, I mean, it probably wouldn't, well, Siva is extremely flexible in the way that you implement it. So we've done this where we're just using the direct equations of motion to compute these terms, but you can pull this out and plug in like an ODE simulator and then take the model and simulate time series. We're currently doing that and trying to optimize finite element models for beam using the SIVA technique. And so that would offer a pathway to do these hard like impact type nonlinearities. Now, also with Eddy, we've done viscoelastic elements where we have extremely high damping and really interesting nonlinearities. They're in general relatively flexible, but there are certainly cases where they would fail.
Mm-hmm.
And I would say SIVA is really more of a framework where you can pull things out and plug other things in. It's not as restricted as Eddy. You could, like I said, you could substitute in neural networks here for some portion of it. You could plug in a finite element model and then update like nodal spacing or nodal locations plus like Young's modulus or something. There's a lot of flexibility in SIVA.
Mm-hmm. Gotcha. Thank you. Any other questions, final questions for our speaker? If not, I guess we can end the discussion here. Thank you very much, Keegan. It was an amazing presentation. And I also thank our audience for the great discussion today.